All right, so it looks like there's a few people in the room that care about their data. That's good to see. So welcome, my name is Peter Morales. I'm a systems engineer for EMC. So I work in the data protection division, and what we basically care about is making sure that you don't lose data in your applications. So today, hopefully you're going to learn a bit about data protection for Hadoop environments. So I want to share a story on how I actually got here. About 12 months ago, I didn't really know too much about Hadoop. And my day job involves architecting solutions for enterprise customers. Most of the time, I'm working on enterprise data warehouse systems or CRM or ERP systems. But more recently, we've been getting requests from customers asking us how to protect data in Hadoop environments. And so some customers even ask us, do we even actually need to protect Hadoop environments, which I kind of thought was quite unusual because no one says they don't need to protect Oracle or SQL or DB2. So I didn't have all the answers, and that wasn't good for my profile. So I spent about 2 months researching Hadoop data protection. And it was interesting, there wasn't a lot of information on the actual topic. And so here's some of the things I found. So there's a lot of different vendors out there that have backup products that protect your traditional application environments. And none of those products actually support Hadoop. So that's the first thing I found. And if you're running an environment where you're supporting these environments, the first thing you turn to is how do you do it in other environments? And there's just nothing available. The other area I found was that Hadoop's size and scale is so daunting that most customers don't even know where to start. There's very few systems in enterprise environments as large as a Hadoop data lake. And then the third point there is that Hadoop already has some inbuilt data protection methods. So I figured that the first 2 points we could probably investigate and we could probably solve. But what I wanted to understand is the last point before I did anything else. And so part of my research, I basically wanted to answer this question: are Hadoop's inbuilt data protection properties good enough? Now, before we explore that question, I want to take you through some of the constraints with traditional Hadoop architectures relative to enterprise architectures. And I want to keep that in the context of data protection. Okay? So this is a kind of a diagram of a typical enterprise application architecture. The blue boxes are the servers, the green boxes are the application storage. And in this particular architecture, there's really 2 ways to protect the data and create copies of the data. You can either stream data via the application servers to any storage, any heterogeneous storage, and they're the grey boxes. So that's what most backup solutions do today for enterprise applications, and that's assuming there's sufficient time and resources to make that happen. This architecture or this strategy, we actually call this a server-centric protection strategy. The other option is to use what we call version storage replication, which is basically those green boxes down the bottom, to create copies and recovery points of the application environments. But what it's actually doing is leveraging the intelligence in the storage system to do that. And we call this storage-centric protection strategy. Now, if we contrast this to your standard like Hadoop architecture, where storage and compute are combined, we can't use storage-centric methods to protect the data because we're basically dealing with plain disk that has no intelligence whatsoever. So this is the constraint we have to deal with in order to come up with a protection process. So given this constraint, another goal that I set myself was to find an efficient method to protect Hadoop using server-centric approaches. I'm going to show you a demo towards the end of this presentation on how we actually, what I came up with and how we do it. So let's go back to answering this question before we move on. So Hadoop has two types of data protection properties, and I've basically classified them into onboard protection and offboard protection. Onboard protection is concerned with protecting data without that data leaving the actual cluster, and then offboard protection is about getting copies of data out of the cluster. If we look at onboard protection first, Hadoop already provides redundancy at the data access layer using a highly available name node. If you contrast this to a traditional application architecture, this is like having redundant storage controllers in a storage system. For the persistence layer, the Hadoop file system implements n-way replication across nodes and racks, all in software. And this is kind of equivalent to your RAID scheme or your erasure coding scheme in large storage systems, right? What Hadoop also provides, which is very uncommon actually in applications, is proactive data protection. So HDFS does not trust the storage that it's actually running on. It basically assumes that disks will degrade over time and that those disks will actually return the wrong data. So the way Hadoop protects against this is it actually generates checksums when data is written to HDFS. It goes and regularly verifies those checksums on a batch basis. And it goes and repairs any corruption from the replication copies. And that's actually, it's pretty good relative to other applications. HDFS also supports read-only snapshots. Just a question, who's actually using HDFS snapshots in the room? Okay, there's a few of you. So there's basically two caveats with HDFS snapshots. And coming from a storage systems background, they basically don't behave the same way. If you look at storage-based snapshots, they're consistent for both open and closed files. Whereas for HDFS snapshots, they're only actually consistent for closed files. And whether that's the way that the developers intended it to be or not, I really don't have an answer, but that's basically the behavior that HDFS snapshots exhibit. So if you want consistent recovery points, and you're going to use HDFS snapshots, you basically need to ensure that files are closed before taking those snapshots. And there's ways to kind of determine that with various Hadoop commands. Also keep in mind that snapshots can be deleted by the data owners, which I actually found this quite unusual when I ran into it. If I'm a super user and I create snapshots, my expectation is that the end user cannot delete those snapshots. But in the case of HDFS, the end user basically owns the snapshots of their data. It also has a HDFS Trash feature, which is very much like your recycle bin in Windows. So that when files are actually deleted, they're not actually deleted, they're moved into trash. And at a later point in time, they're actually expunged. There's a few things to keep in mind with this particular feature. it's actually not implemented in the core HDFS file system. It's actually implemented in the HDFS client, which is good and bad. So basically, it can be overridden. So if a user wants to override the trash feature, they can. And the user that actually owns the files can empty that trash bin at any time. So it's not necessarily the best thing to rely on from a data protection perspective. And if you're manipulating or deleting files some other way, whether it's through your own program or API, then you're probably not going to have this feature available to you. So they're the onboard protection properties that come with Hadoop out of the box. If we look at offboard data protection, this is provided using what they call Hadoop distributed copy. This basically lets you create copies of HDFS files to a variety of different targets. So you can create a copy to another HDFS cluster, but you can also create copies outside of HDFS to, say, an S3 compliant object store, or OpenStack Swift, FTP, and in the latest version of Hadoop, Azure. Distributed copy is actually quite good in that it actually distributes the workload amongst the nodes. So it can scale with your cluster. However, each file copy is mapped to one node. Now, it's normal to have very large files in Hadoop environments. So if you think about the consequence of this, a single file copy, the performance is actually bound by the network on that one node that it's going out on. As an example up there, about a 10 terabyte file with a 1 gig interface is going to take you 22 hours to copy that file, which is, quite a long time. So now we know what Hadoop provides out of the box with respect to data protection. So we need to now kind of ask the question, what are we protecting against? And how do Hadoop's inbuilt properties fare against the different events? Because that's really what's going to allow us to decide what we should do. So I don't expect you to read that. You'll get a copy of these slides. So this is a data loss event matrix. This is something actually I use in my day-to-day job to assess, enterprise data protection strategies. On the left, your left, we have the events that can lead to data loss. And this is not just applicable to Hadoop, it's applicable to any enterprise application. To the right of that, we have a rating system. I'll talk a bit about that later. And then to the right again, we have features and properties applicable to the various different data loss events. And then to the far right, we have concerns relative to those features and events. And so when I put this matrix together and I assessed, all the different inbuilt data protection properties that Hadoop provides, I basically concluded, and your conclusion may be different, it really depends on your environment and your operational skills and any other defenses you put in place. But I basically concluded that Hadoop fares very well when it comes to data corruption, when it comes to things like component failures, infrastructure software failures, such as firmware failures on servers. But it has some risk when it comes to operational failures, site failures, which is fairly obvious, users that actually do the wrong thing or just make mistakes, application software failures, and I'll talk a bit about that later, malicious user events, and malware. So these are some of the events that can lead to data loss. So we have to think about them. I'm also a big believer that software is not immune to failure. And so I'll give you some examples. There was a study done that was published around for Yahoo's Hadoop environment where they studied the integrity of the data. What they found is they lost 650 blocks out of a population of 329 million. Now, that's actually a phenomenal achievement. That's not a bad thing. But if you look at the causes of the loss, 85% were due to software bugs in Hadoop, and 15% were due to single replica copies. And that last point is very interesting. What does it mean? It means that someone just went and altered the replication factor for a particular data set. And for me, that was a little bit troublesome, because what I found is when I looked at it, it's actually difficult to enforce data protection standards in Hadoop. You can set things like replication factors as a default, system-wide default, but data owners can actually go and change that for their own data sets retrospectively. So that's something you need to think about. It's something you can audit and track to see what users have actually done so that you can go and change it back. But at this point, it's difficult to enforce standards like replication and redundancy. Another example, and I don't want to, alarm you guys. I also did find one known open condition in the Hadoop Apache code base that causes blocks to be lost. It's very rare. It's still open. If you want the details, look up that Jira note. It basically makes some assumptions around POSIX schematics around the file system that HDFS is running on, but I won't go into it. And then there's a new thing to keep in mind. As of the 2.7 release, HDFS now supports truncate operations. Previously did not support this. And in the past, we basically kind of made the assumption that Hadoop was immutable, right? And now with truncate, that immutability no longer exists if it's turned on. So that's not valid anymore. We can't rely on immutability as a form of protection, right? The basic moral of the story here is that plan for software failures, plan for human failures, and if you think your data center is going to blow up or you're going to lose power, plan for site failures. But what I would say is, because you're dealing with huge volumes of data, you have to be sensible in your approach. Not all data is going to be created equal in a Hadoop cluster. So only protect the data that you determine is valuable, and only protect what can't actually be derived, again, in a reasonable time frame. So if you have result sets that you can recreate quickly, perhaps you don't need to protect them. But you do need to protect the sources for those result sets. So these are kind of my 3 guiding principles for data protection strategies, and these are applicable to Hadoop or any other enterprise app. Diversify your protection copies. So the analogy I use to explain this is basically investments. If you go and invest your own money into, let's say, stocks, you typically will hedge your risk by spreading those investments across different asset classes. And we should do the same with data copies, right? So the message is keep your protection copies on a system, or keep at least one, on a system that is diverse and different to the source system that you're protecting. So that's kind of rule number 1. Rule number 2 is we want to maintain logical and physical isolation so that problems that impact the source system cannot propagate to the target system. And really, for this rule to be successful, we need to have, what I call separation of concerns. The rule here is the system protecting the source data should not trust the source system. And this is applicable when you're doing things like HDFS to HDFS distributed copy. There's an implicit trust relationship there, which can be used to compromise the target system. The last rule is we want our protection copies to be frequently verified. So just like HDFS verifies the data on a regular basis, we don't want to assume data is written correctly or stays correct on the protection system. We need to regularly verify the data, but we actually need to do it in an automated way, otherwise it would never scale. So here's this very simple sample strategy that you can use that aligns the protection method to the value of the data in your Hadoop cluster. So data that is desirable, that little circle down the bottom, you may just decide, I could protect that with the HDFS Trash. Or data that is necessary, you may actually protect it using two methods, HDFS Trash and Snapshots. The list goes on. But what I would say, if you have critical data stored in Hadoop, you should actually use all methods available to you within the Hadoop ecosystem. But you should also use version copies to a diverse and different storage target, right? To address those three principles that I talked about. So now what I'm going to do is demo how you can use Hadoop distributed copy to create versioned copies to our EMC data domain storage system. Data domain is what we class our protection storage platform. It's frequently used to protect traditional enterprise apps like your RDBMS systems and so forth. And it's got a few unique properties. One is all the data that lands on a data domain storage is deduplicated. So if you're creating copies of the same thing over and over again, it's actually quite efficient and can store that data very densely. And it does that all inline. The second thing is it has very strong data integrity properties that I talked about previously. We basically verify integrity in real time as the data lands on the system, but we also go and verify the integrity to address latent errors as well. And the last point there, it's really fast. It's really fast. It's designed to ingest streaming data at really high speeds. Some of our largest systems can do anywhere from 22 terabytes an hour to 54 terabytes an hour. So the approach I'm going to show you, what's unique about it is we're going to use distributed copy with what I call an incremental forever technique. And what we're going to do is we're going to maintain multiple version copies of Hadoop datasets on the data domain storage. The reason the incremental forever technique is important is because we can create these copies and keep the amount of time it takes constant relative to the amount of new data entering your Hadoop cluster. So let me just switch gears now. Let's see if this works. So I've got, what I've actually got running here is the HTTP sandbox. And I've got a data domain emulator running in a virtual machine. I should have started those VMs before okay. So first thing I'm going to do, did that come up? Good. Is log in to the sandbox. And I'm going to mount the data domain system over NFS to my Hadoop data node. Now I've only got one data node. If you have several data nodes, then you'll do this across all data nodes. Then as the HDFS user, what I want to do is create protection copies of some web logs in the HDFS users directory. So these are the 2 web logs, and we basically want to create copies of these on a regular basis. Now what I've got is a couple of helper scripts to make this demo run a little bit faster. So the first thing I'm going to do is run distributed copy using these helper scripts of the web logs to the data domain storage. And this is kind of my data domain interface here. I'll probably have to log in again to it. Yep. This is the system manager. And what I can see is the I/O activity occurring as the distributed copy is actually running. You can see the disk activity. Now, because the data is actually being deduplicated, you won't see a lot of disk I/O because all the deduplication happens in NVRAM. And then you can see the network activity. So you can see a lot more network activity occurring and a lot less disk activity, right? Because the data is very compressible and it can be deduplicated quite easily. So now I've created the copies actually being created. And what you can see here on the statistics on the data domain system is 2.39 gigabytes was ingested. Obviously this would be a lot larger in a real environment. But we're only storing 0.33 gigabytes. So it's basically with that first copy, it's reduced the amount of capacity down by 7 times. And that's due to the dedupe algorithms that we have in the system. Now what I want to do, now that I've established that baseline, I actually want to preserve that baseline. So I'm going to run what we call a fast copy. And this is actually going to create a new copy of what we just created on the data domain system, and we're going to give it a timestamp based on the current timestamp. And as you can see, it's instant, because all it's doing is it's actually creating copies of the pointers to the data, and all the data is deduplicated. And what you'll notice, if I refresh this screen, the amount of logical data we're storing actually doubled. But the amount of data we're actually storing on disk didn't even change. Right? So this is what allows us to create multiple version copies. Now, what I also want to do now is add a new weblog to the HDFS file system. So I'm just going to use this little script. It's going to go create a new weblog. And let's just verify that that happened. So you can see previously we had 2 weblogs, now we've got 3. So now I want to run another distributed copy because I want to refresh my baseline. Let's say this is the distributed copy I run the following day because I want to create recovery points every day. So I run that distributed copy, and now what this will do is it's going to recognize that on data domain we've already got the previous 2 files, and it's only going to add the 3rd file, right? So essentially that creates an incremental forever strategy where it's keeping the source and the target in sync. And you can see here it skipped the first 2 files and it copied a new file, right? So now that I've done that, I want to preserve that version, that baseline on data domain again, right? because this is my Tuesday version. So I just run a fast copy again. And again, it will instantly create another version of the data on data domain. And if we actually look at the data domain system to see how many versions we're now storing, they're all available to you. Right, so you can see here, I'll expand the screen a little bit. This is the actual where the disk CP actually writes the baseline and keeps updating that baseline. And these are the copies we actually created with the different timestamps. Right? So now these are our recovery points. And we can go back to these recovery points and at any time. We can even run map-reduced jobs directly from these copies because all the data nodes have access to the data domain system. So if we wanted to get the data back to run one job, it probably doesn't make a whole lot of sense to copy it back into HDFS. You could actually just run the job against the data domain system because it is very much designed for sequential I/O workloads. The other thing that's important though is separation of concerns that I talked about previously. We want to make sure that these version copies cannot be removed, right? So we want to eliminate that trusted relationship between HDFS and your target storage system. So one of the features we have in data domain is a feature called retention log, which is very similar to the worm feature, if you've heard about worm intake, which is write once, read many media. Basically means that once I lock these files for a certain amount of time, they cannot be deleted, right? So I'm going to do that now. I'm going to lock let's say this one here. If I can get my mouse to work. And what I'm going to say is I want to lock it for 10 days from today. So no one will be able to delete it until those 10 days actually expire. And it's done. They're locked. The way we actually lock it is we just set the access time to 10 days in the future. The data domain system recognizes that and ensures it can't be deleted. So just to kind of prove that to you, and hopefully this demo doesn't all fall over and allow me to delete the files. It won't let me delete them. So I've basically eliminated the trust relationship between HDFS and the protection storage so that even if HDFS was compromised or Hadoop was compromised, they can't get to the protection copies. So in summary, by leveraging the data domain technology and combining that with distributed copy, you can actually create an incremental forever data protection strategy for very large Hadoop cluster environments. So that we've got 6 minutes left. There's a lot more information available on this talk on my blog. So if I can actually find the So that's my blog link there. If you look that up, you'll find other things that I couldn't fit into a 40-minute talk, but I'm happy to take any questions now. In the back.
You started by comparing with traditional RDBMSs. They've had a concept of point-in-time recovery for a long time.
Yep.
That's something which you explored either for Hive or HBase over here.
Sorry, what was the question?
So point-in-time recovery for HBase or Hive.
Yeah. So HBase has its own snapshot capability, but again, it has similar problems to HDFS snapshots in that they do not guarantee consistency.
I mean, that is only the point when the snapshot was taken, right?
Yeah.
If an accident happened after that, so in order to roll forward from the snapshot time to when the accident happened.
Yeah, I haven't explored that specifically.
Thank you.
Question? I think so. The question's about Ambari reporting blocks are corrupt and then they're not corrupt. Is it? It's probably something you should talk to the Hortonwork guys about. If it's not corrupt in HDFS and you know the FSCK is passing, it may be some issue with Ambari reporting the wrong status. Yeah, as far as I know, the FSCK command is what goes and validates the file system. You can also use FSCK to determine files that are open for write. So if you do a snapshot and you want to make sure it's consistent, you can actually run that before you do the snapshot. Work out whether those files are actually open for write. If they are, wait till they're not, and then do the snapshot. Another question? So the question was the tools that, those little scripts, whether they're specific to data domain, they are today. It was actually, I just wrote them for this demo, just to simplify it, but essentially they just run standard Unix commands, both on the HDFS client, and they actually also run commands on the data domain system to trigger things like the fast copy operation, and that's about it. Yeah, so the question is, when I calculated the storage, did I consider all the different versions? The answer is yes, because the data is actually not changing. In data domain, we just actually store pointers to the same data blocks if those blocks haven't changed. So when you think about creating multiple copies of the same thing, if you did that on a traditional storage subsystem, you're going to use up a lot of capacity. Whereas data domain is specifically designed to eliminate all the duplicate data and only reference it once. Any other questions?
So one correction to your talk. You actually can enforce minimum replication of blocks at the name node level.
At the name node level?
Yes.
And you can't retrospectively change it?
No.
Okay.
You can go higher, but you can't go lower.
Okay, cool. And Shailesh, you were just going to mention something?
Hey guys, so I'm the product manager for this product. So just to kind of give you a little context, this solution is a GA solution, and we currently support Cloudera, Hortonworks, and Pivotal distribution. So if you guys have any questions, you want to get some more information, please feel to reach out.
Okay, anything else? Thank you very much.